Alright folks, I think it's time to get started. Welcome back. This is the last week of class. Can you believe it? I can believe it. We have I sent an email earlier this morning about my plans for the week. So what I said was, today I want to do some extra examples from the sections for this week, which is about fundamental theorem of calculus and the area, finding areas using the integral. And then tomorrow I'm going to just do like a review for the final exam. And then Friday is going to be our normal kind of quiz and homework day. So everybody will finish up on the last homework assignment and work on the quiz. I hope that everybody is feeling good towards the end here. Like I said before, I would be happy to send you a report of what your grade is at this point if you just let me know by email, and I will send it along to you. Does anybody have any questions before we get going about the end of all things? The end times. All right, let's just do some examples then from the last two sections. These are about using the fundamental theorem of calculus, which is important. Did somebody say something? No. All right. Fundamental theorem of calculus. Sounds important, and it is. Calculus. It is important. The fundamental theorem of calculus is, it tells you how to find the true value of the definite integral. This is what it says. The integral from a to b, f of x dx, is the, it is this. Well, I'll write it first and then I'll explain. F of b minus f of a, big F, where big F is the antiderivative of the little f. Alright, and this finally is the connection between the antiderivative and the integral. That is the indefinite integral and the definite integral. The definite integral is the area under the curve of something. The indefinite integral is the antiderivative, which is totally different. Why they are both called the integral is because of this. This is the relationship. The left side is the area under the curve of something, and then the right side is the antiderivative with just two different values plugged into it. Alright, so this is the relationship between the area under the curve and the antiderivative. Alright, let's just do some examples. So I have a few examples of this, and then I also want to talk about some examples from the other section, which is just about using this to find areas of curvy regions. Any questions about that before we get going? Alright, let's get going. How about the integral from 2 to 5 of x squared plus 2x to the 4 plus 7 dx? All right. In the previous sections for the past week, we have been talking about methods for estimating this using the rectangles, the left endpoints, the right endpoints, the midpoints, or the Simpson's rule, the trapezoid rule. Those are all estimations. Using the fundamental theorem of calculus, you can find the actual answer here. You might, I don't know if you ever wondered, why did we talk about those estimations if we were then immediately going to talk about how you find the true answer? What's the point of estimating when you have a method for finding the true answer? This method works only when you know the equation and you can find the antiderivative. But as I've said in the past, in the real world, you usually want to do these things for things where you don't know the equation. All you have is like a graph of something or a bunch of data points of something. In that case, you have to use the estimations. You cannot use the fundamental theorem. But anyway, if you know the equation, you can use the fundamental theorem. Here's how we do it. It is going to be the antiderivative with a 5 plugged in minus the antiderivative with a 2 plugged in. The way we're going to write this is first we find the antiderivative. Can anybody shout out the antiderivative of that function?
A third x cubed plus 2 over 5x to the 5th plus 7x.
Excellent. I like that. I hope you remember how to do the antiderivative. it's that. This is a fairly easy example of doing an antiderivative. Okay, that's the antiderivative, and then I'm going to put this bar here with a 2 and a 5. All right, the bar indicates that in the next step I intend to plug in a 5 first, and then subtract, and then plug in 2. All right, this bar is really only used when you're doing the fundamental theorem of calculus. So this integral sign here means, of course, the area under the curve. You don't write the integral sign here because I just did the antiderivative, but you write this just to remind yourself of what you're about to do, which is I'm going to plug in 5 and then subtract and plug in 2. This bar always goes at the end rather than at the beginning. The integral sign always goes at the beginning. The bar here always goes at the end. Anyway, what is it? I plug in. I get 1/3 times 5 cubed. I'm plugging in 5 everywhere. Plus 2/5 times 5 squared plus 7 times 5. All right, that was, you know, in the theorem here, that was big F of 5, right? And then I go minus. You better put parentheses here. 1/3 times 2 cubed plus 2/5 times 2 to the 5 plus 7 times 2. I plugged the 2 in everywhere. All right, and that's the answer. This is the actual value, the exact value of the area under the curve. If this were on a test or something, I would expect you to just leave it at that. You don't have to try to compute those numbers. If you want to, you can plug that into your calculator. You should get a specific number. All right. I did not plug this into my calculator. Any questions about that one? This is an easy one.
For the first part, isn't it 2/5 times 5 to the 5th?
Yeah. Thank you. I made a typo right here. This 2 power 2 should be a 5. Yeah, I'm just copying this whole thing and plugging 5 in for x. Thank you for that. I will fix it. 5. Did I mention, sorry, I meant to say at the beginning, I hope that you will take some time to fill out the class evaluation. I hope you'll forget that little typo that I just did. Don't mention it on the class evaluation. You will find a link to the evaluation survey. It's, you know, I'm sure you've done it in your other classes also. It's an online thing. You will find a link near our homework assignments. And I hope that you will be able to take some time and do that. I think I would rather not set aside class time, since our class time is already fairly unstructured. But I wanted to get in the problems for today and the test, the final exam review session tomorrow. So please visit that link and do the class evaluations when you are able. I do appreciate any comments that you have about the class. Sorry, I forgot to mention that before. All right. Great, let's do some more. So that was a fairly simple one because just a polynomial. Here's one that's not really much harder, although you have to remember how to do it. Integral -1 to 3 of 2 to the power 3x dx. How do you handle, you know, my first step is to write the antiderivative. How do you do the antiderivative of 2 to the power 3x? You have to remember, we got rules for this sort of thing. There is a rule like this, a to the kx, the integral of a to the kx. And it is, I don't know if you remember this, but it is 1 over k ln a times a to the kx. All right, now when we write this antiderivative rule, we put a plus c. As I said in the video, you don't have to put the plus c when you're doing the fundamental theorem of calculus because the plus c will always end up canceling in the end. So it just doesn't matter at all. All right, so I'm going to use this formula over here to do this antiderivative, where playing the role of a is this number 2, and then the k is 3. So it becomes, I'm using the answer over here, k is 3, a is 2. 1 over 3 ln 2, 2 to the 3x. And then, and then I put the bar, -1 and 3, all right? This is the fundamental theorem of calculus. You do the antiderivative first, then you put the bar, and then you're ready to write the answer, really. The final answer, I'm going to plug in 3 for x, and then subtract and plug in -1 for x. So I go 1 over 3 ln 2, 2 to the 3 times 3, minus 1 over 3 ln 2, 2 to the 3 times -1. And this is the answer. Again, I would expect you to just leave it like that on a quiz or a test. If you want to, you can plug it into your calculator. You should get a number, a specific number as the answer. Any questions about that one?
Do we have to put parentheses on the last thing that you just subtracted?
In this case, the parentheses are not necessary. The reason I said you need them in the previous problem, for all you haters out there, it's because I have pluses in here, all right? Which means any minus sign on the front actually should be distributed across these three things, right? And that's what it means when I write it with the parentheses the way that I did write it, and that is correct. If you omit those parentheses, then the minus sign will only be on this guy, and these others will be pluses, which would be wrong. There's a different answer if you have no parentheses right here. It doesn't matter in the current example because there's no additions in here. That's just one thing with multiplications but no pluses, which means this minus sign does not need to distribute across anything, so you don't need the parentheses. If this is, you know, this is something that hopefully you learned all about in high school or maybe even middle school. But if you're still a little unsure about that, you can put these parentheses. Like if you put the parentheses here, it's not wrong. It just doesn't matter in this example. In the previous example, these parentheses here really do matter. In this one, they don't matter in this one, but they're not wrong if you want to put them in there. Any other questions? All right, let's do some more.
I have one other question.
Oh yeah, sure.
So why do we have to put parentheses on the second thing that we're subtracting, but not the first? Like if we look at the first one that you just did, why do we not put parentheses?
So the purpose of the parentheses is to make sure that this minus sign distributes onto everything. That's the only reason these parentheses are important. And since there is no thing out here that needs to distribute on this first part, then the parentheses are not necessary on the first one.
Okay, thank you.
Yeah, I love the parentheses questions. Keep them coming. I'm a parentheses lover, not a fighter. All right, let's do another one. This one is actually considerably more difficult than the other two. X squared times x cubed plus 1 to the 4 dx. All right. Integral 0 to 3 of x squared times x cubed plus 1 to the 4. What makes this one, I said this one is considerably harder than the other two. What makes it harder is because you have to do the u substitution in this one. That thing on the inside of the integral is too complicated to just immediately say what the antiderivative is. So you got to do the substitution. So I hope you remember how to do the substitution. Our strategy when you're doing the fundamental theorem of calculus in one of these guys is I'm going to do the entire substitution first. I'm going to do the entire antiderivative first, the whole u substitution, everything, all the way to the end of that. And then finally at the end I'm going to plug in the 3 and the 0. So let's see if we can make it happen. I begin by choosing an appropriate u. Any u sub masters out there? What should I choose for the u here?
X cubed plus 1.
Yeah, you want to choose something which is on the inside of something. So x cubed plus 1 sounds like a good idea to me. And then we find the du. In this case, it is 3x squared dx. Remember, I hope you remember how to do this. The du is always the derivative of the u. And just because I know we usually have to do this, and in this problem we do have to do this, I'm going to divide the 3. 1/3 du equals x squared dx. Remember, in these problems, you often have to divide the constant right there. And that is going to be important in this one. Okay, so when I do the substitution, I get down to integral of, I'll begin by just plugging the u in directly where it goes, right? X cubed plus 1 is the same as u. So I wrote the same thing, but I just put u instead of x cubed plus 1. What I would typically do next is, I like the u part. I don't like that x squared still hanging out, so I'm going to write the u thing first. And then what remains to be substituted is x squared dx. And what is x squared dx? It's right here. It is 1/3 du. So this is integral u to the 4 times 1/3 du. And now I have substituted all the x's away and replaced it by stuff involving u's. now we can do the antiderivative. So I'm going to move the 1/3 out. That's what I would usually do to prepare for doing the antiderivative. And now do the antiderivative. I got 1/5 u to the 5. All right. Plus c, of course, but since I'm doing the fundamental theorem calculus, I'm not going to put the plus c because it doesn't matter. It will cancel out in the end anyway. All right. And one final step for u substitution is always to replace the x's rather than the u's. So this, would you mind if I multiply 1/3 times 1/5 is 1/15? And then I got x cubed plus 1 to the 5. All right, I replaced the u with the x's. All right. This is the u substitution. This is a fairly standard u substitution, I guess, but these are tricky, and if you haven't done it in a couple weeks, you may have to review yourself. All right. Anyway, I have done the full u substitution, which means my original integral then is integral 0 to 3 x squared x cubed plus 1 to the 4 dx. It is 1/15 x cubed plus 1 to the 5, plugging in 0 and 3. All right. Remember I said I was going to do the substitution completely to find the antiderivative. That's what I just did. The antiderivative is 1/15 times x cubed plus 1 to the power 5. And then, at the end of all that, I'm going to plug in the 3 and the 0. So, here we go. Let's plug them in then. I get 1/15, 3 to the 3 plus 1 to the 5, minus 1/15, 0 to the 3 plus 1 to the 5. And this is my final answer. Any thoughts about that one? This one's a little tricky. A lot of steps. This is how you do the fundamental theorem in a problem which requires u substitution. All right. I'm satisfied with that. So these are all the examples that I wanted to do concerning the fundamental theorem of calculus. That was whatever the second to last video. I don't remember the numbers. And then the last video, the very last video, is about using the definite integral to find the area of certain curvy shapes. So let's see if we can do a couple of those, and that'll do us, I think, for the semester. The very last video is about areas. Let's see. So I got two problems to do. The idea is, finding the area of something. The integral, the purpose of the integral is it tells you the area under the curve. So we can use the integral to find the area of certain shapes. Let's find the area between the x-axis and this curve y equals 9 minus x squared. All right. 9 minus x squared. So this one does not come with a picture or a description of which x values to use. So what we want is, we want to set this up like this: integral from something to something of 9 minus x squared dx, right? The question is, what are these guys, these numbers? All right, what are we going to use for those values? They would describe geometrically where the x's go in this region, the area that we're trying to describe. Now, because I know something about functions, this 9 minus x squared, I happen to know, is a parabola because it's a x squared thing. And I know additionally, because it has a minus sign in front of the x squared part, it means a parabola goes down like that, right? Rather than up like this. So the picture here, it looks like something like that, right? It goes down rather than up because I see a negative coefficient on the x squared, okay? And so I suppose the area that I'm looking for is this area here. All right. The question still remains, though. I need to find these 2 points. What are those 2 points? those are supposed to go in these, you know, that's what these numbers are really. Can I connect these up here? Sorry, my squiggly lines. That's what those numbers are supposed to be. What do you think? Anyone want to suggest? How can we actually find those numbers?
You set them equal to 0 and find the x.
Yeah, those numbers are the x-intercepts of this graph, right? And so we can find them by setting y equal to 0 and solving for x. So these are the x-intercepts. And the way to find those x-intercepts is we set y equals 0, solve for x. All right, let's do it. Y equals 0, solve for x. So I go 0 equals 9 minus x squared. And then can we solve this for x? I think we can. If you add the x squared over to the other side, it says x squared equals 9. Take the square root, I get x equals plus or minus 3. Don't forget the plus or minus. You expect to get 2 answers here. And that's why you need the plus or minus in order to get the 2 answers. All right? I feel pretty good about that. So the question then, or my answer really is this integral, negative 3 to 3, 9 minus x squared dx. Of course, that's not my final answer. This is how we get started to actually work the equations, and eventually we will get the answer from here. All right. This is kind of a lengthy setup, but it boils down to an easy integral. As far as integrals goes, this one is pretty straightforward, I think. What do you say? What's the antiderivative?
9x minus 1/3 x cubed.
9x minus 1/3 x cubed. I agree. And then I got to plug in 3 and minus 3. You always plug the top one in first. So I go 9 times 3 minus 1/3 times 3 to the third minus parentheses 9 times negative 3 minus 1/3 negative 3 cubed. And that's the answer. If you want, you can plug it into your calculator. You should get a number. Whatever that number is actually the area of that red shaded region. All right. What are your questions about this one? In these problems, typically the integral itself will not really be hard to do. It's just a question of setting it up properly. All right, let's do one more, and then maybe we'll have some time to get started on the homework. So I don't know if you've already looked at it. Okay, this one is a little trickier. Find the area between the x-axis and this function, y equals 2x plus 4, on the interval negative 3 to 0. All right. This one I actually told you the interval of x values. It is x going minus 3 up to x equals 0. The thing that makes this one a little tricky is the region itself is pretty weird looking. In this case, the function y equal 2x plus 4, I happen to know what the graph of that would look like. It's a line with slope 2 and y-intercept 4, so it looks like this, right? This is what the graph looks like. I only want to consider from negative 3 up to 0. So negative 3 would be over here, I believe. And so the area that I'm considering here is going to look like this. It's got like two pieces to it, right? At least it might. I mean, are you really convinced that this point where it goes through is actually in that range? I mean, if that point where it goes through is all the way over here, then you would only get, it would look different. So in order to do this problem, you really need to understand a bit about what this graph looks like and what the shapes look like. The reason you need to understand this is because, let me just say, you can't just do integral minus 3 to 0 2x plus 4. This would be easy. But this will give you the wrong answer, and the reason is because when you do an integral, it is measuring the area under the curve, but this is sort of a technicality that I mentioned in the videos. It hasn't really come up much. It matters in this section though. when you measure the area under the curve using the integral, an area above the y-axis will be measured as positive, and an area below the y-axis will be measured as negative. And so when you do the integral here, it's going to measure this part as like a positive area, and this part as like a negative area. And when you do the entire integral here, those areas will be added up, and they will kind of cancel each other out. Now I'm not saying you'll get 0, but there will be some amount of partial cancellation. The true answer here that you get if you do this will not actually be equal to this red area. It'll be something like one of these, it'll be like this triangle minus this triangle, which is not what you want. I want actually the area of the two triangles as triangles, right? So what you got to do is break up the integral into two parts, do them separately, and then add up, make them both positive and add up the answer. So we split the integral into two parts. This is our strategy. Split it into two parts, do them separately, and then add, and then let me say, make the answers positive, and then add them together. We have to make them positive because one of them is going to end up being negative, but we don't want to count it. We don't want to count it as negative. We want to actually find the real area, which is to do that. You just make it positive and then add them together. Okay. A preliminary consideration is if I want to split it into two parts, you need to know exactly where is this point, the point at which I'm going to split the interval up. There's one sort of piece on the left side and then another piece on the right side, and we have to do them separately. Where is that point? Again, you find this as a x-intercept. So this is the x-intercept. What is it? You find it by setting y equals 0 and solving for x. So I go 0 equals 2x plus 4 using the formula at the top you see there. Y equals 2x plus 4. I'm finding the y-intercept, the x-intercept means plug in y equals 0, solve for x. What you get 2x equal minus 4, right? Divide by 2, x equals negative 2. So that point right there is actually negative 2. And so what I meant when I said split it into two parts, we'll do the integral from minus 3 to minus 2 of this function, 3x plus 4. And separately, we also do the integral from minus 2 to 0, 2x plus 4. All right. One of these will be negative. Actually, if you believe my picture there, this first one will be negative. We're going to make it positive and then add them together because I don't want them to cancel each other out. I want to get actually the total sum area of both of them. All right? All right, let's do it. So I'm going to just do these two integrals separately. 2x plus 4. What do you get? You get the antiderivative is, antiderivative of 2x is just x squared, isn't it? Plus 4 becomes 4x. All right, and I'm going to plug in minus 2 and minus 3. What do we get? Minus 2 squared plus 4 times minus 2 minus 3 squared plus 4 times minus 3. Now, ordinarily, I would just leave my answer like that, but I want to figure this out so that I can make it positive and then add it on to the other one. So this, I'm actually going to compute this all out because I need to see what the number is in order to make it positive. It's I know it's going to be negative. If you do it right, it's going to end up being negative, but I want to see what it is so that I can make it positive again. All right, simplifying. 4 plus, this is negative 8, right? So it's 4 minus 8, and then minus, in the parentheses, 3 squared is 9, and then minus 12, right? What is that? 4 minus 8 minus 9 plus 12, which is 4 minus 8, negative 4 minus 9, negative 15. Negative 3? I think it's negative 3. Anybody disagree? I think it's negative 3. All right, and so on the picture, remember the picture had like these two regions, right? So this one has area 3, right? When I did the integral, I got -3. That means the area is 3, and it's below the y-axis. Okay? In my final answer, I'm going to add this 3 plus whatever the other area is. All right, let's do the other area. The other area will be the same integral, I mean the same function, but it's -2 to 0 this time. 2x plus 4. And what do we get? It's the same antiderivative. It's x squared plus 4x. Plug in 0 and -2. Plug them in. I get 0 squared plus 4 times 0 minus -2 squared plus 4 times -2. And what is that? This is 0, 0, minus, okay, here is 4 minus 8. 4 minus 8 is -4, but there's another negative there. I get 4 for this. All right, so that means that the other triangle, this one, has area 4. And so, in conclusion, the total area is 3 plus 4, which is 7. That's my final answer. All right. It's a bit of a journey to get there, but that's how we do it. Are there any questions about this one?
I know it doesn't matter much, but why is the first half 3?
Why is it?
Yeah.
Did I
might have done it wrong, but I got -1 and then changed it to 1.
Okay. It's possible I messed it up. Where did you go different from me?
I just did like 4 minus 8 is -4 minus 9 is -13 plus 12 is -1.
Oh yeah, I don't know what I just added the numbers up wrong. Thank you for that. So yeah, this is, anyone else agree? This is -1. I think he's right. You all know by now I'm not really great with numbers. I tell people that and they don't believe me. It's true. Okay, so that has area 1. So down here at the bottom, it should be not 3 plus 4, but 1 plus 4. Thank you for that. 1 plus 4, which is 5. How you like me now? I think that's right. Any other questions about this? It is a little tricky.
I have a question.
Yes.
Oh, sorry.
No, go ahead.
So why don't we? So we have to put when we split up the equation, we put the -3 and the -2 in the same like integral because it has to be in the same order on the number line. Or I don't know if that makes sense, but I'm just confused.
Yeah.
I got lost there.
Yeah. So it's like my picture is well, in this case, it's over here. The curve looks like that, and I have these two. This is probably a better, more accurate scale here. If you want this area over here, so that number is -2, this is -3, and this is 0. If you want that area, you do integral -2 to 0 of my function. It's because these numbers here, they always represent where the x values go from. The smallest x value in this shape is -2, and then it goes up to the largest being 0. And then this other side here, how would I do that one as an integral? It would be from -3 to -2 of the same function. So yeah, I would say it's something like, because this is the order in which the numbers go. You know, you go from -3 to -2, and then you go from -2 to 0. I'm not sure that's a satisfactory answer. That's how I think about it.
Yeah, that's good.
Yeah.
Thank you.
All right. We got 15 more minutes on the clock. I don't have any more examples that I wanted to go through though. So if there are no more questions for the large group, maybe I will put you guys in small rooms so that I can talk individually with folks. I don't know if you've started working on the homework. How about this? I'm gonna if you don't want to do that, since I've got you here, I am going to put in the chat a link to the class evaluation thing, and maybe the next 14 minutes would be a great time that you could do that.
Could you do one of the homework problems for like the class?
Yeah, sure.
Okay,
You have one in particular?
yeah, could we do 44 on from section 7.4?
I'm getting my book. $44. Ah, yes, this one's a little weird. I was going to suggest that I would do one, not the same one that's in the assignment, just because I usually like to leave those ones for you guys to do. I'll say, maybe I'll say some words to get you started on it. Would that be helpful?
Yeah.
So this one, number 44 in the book, has a very weird picture. So it says find the shaded area. And then they actually give you a picture, which is nice. It's nice when they give you the picture because then you don't have to like figure out yourself what the picture is supposed to look like. Here's the function is y equals ln x divided by x. And that function looks something like this. And the shaded area is this. I'm doing it in blue because it's in blue in the book. It's like that. And then there's another sort of section like this. And, oh, what? A beautiful picture. Okay. And the picture also has mysterious annotations on it, which are actually very important. This is 1, and over here, they say this, 1 over e, and over here, it says e. And they're written in weird positions. The e is written up there. But what those are the x values of this shaded region that you're supposed to be doing. So this right here is the number e, and that on the left side is the number 1 over e. I don't know if that is a little confusing when you look at the picture, but this is how you should interpret the picture. So what you got to do is the integral, divide it into 2 parts, just like the example that we just did. We have the one on the left and the one on the right, and so the left side you're going to do the integral. And what are the boundary values for the x? The lowest x value is 1 over e, and then the upper x value is 1, right here. That's this interval. And then of the function, ln x over x. And then this region will be the integral from 1 to e. The lower value is 1, the upper value is e, of the same function, ln x over x. dx both times. All right. And you're going to notice, if you do it correctly, this will be negative, this one. And you're going to have to make it positive and then add it onto the other one. And to do each of these integrals, you're going to use the u substitution, which adds another extra layer of complication to this problem. Is that helpful, or do you want me to say more than that?
Could we do a little bit more?
Do a little bit more. Okay, let's do the one on the left, and I will leave the one on the right for y'alls to do. All right, the one on the left. Let's see if we can do it. It shall be integral 1 over e up to 1 ln x over x dx. All right, we don't need the picture anymore. We just have to do this integral. We're going to do the u substitution. This is a weird one because there is no like inside of anything to choose for the u. In such a case, often when it's a fraction, I choose the denominator. But actually, in this case, choosing the denominator will not get you anywhere. I think I mentioned in the video that choosing u equals x is never a helpful substitution. It never works when you're doing the u substitution. Your only other option really is to choose the u to be ln of x, and let's just see what happens. This is a strange example, but I'm just trying my best here. I'm just a simple man trying to make his way in the universe. What do you get for the du then?
Would it be 1 over x?
It would be 1 over x. That's the derivative of ln x. So 1 over x dx, of course. Actually, I like the way this is beginning to look because the other part of this, like the top is the u, the other part of it does look like, you know, x in a denominator. So I'm feeling pretty good. I will begin by, as always, I just put the u where it goes, right? U is ln x, and so I replace ln x by u. And then I'm going to try and separate out the u stuff from the x stuff. And in this case, the way to do that is write it something like this as a multiplication. U times 1 over x dx. And what is 1 over x dx? It is du, isn't it? So this is integral u times du. All right. And now we can do the antiderivative, right? Here I have just u. So the antiderivative will be 1/2 u squared. This is just like the antiderivative of x is 1/2 x squared. But, you know, this time the variable is called u. 1/2 u squared is the answer. And then to complete the u substitution, I replace the u's with the x's. So 1/2 ln x squared. All right, and now finally, this being a fundamental theorem of calculus question, I'm going to try to plug those two values in. What do we get? 1/2 and then ln of 1 squared minus 1/2 ln 1 over e squared. And like I said before, ordinarily I would expect you to just leave this like this, but we want to actually compute these because we intend to add it together with the other part. You can plug this into your calculator if you wanted to, but it's not really necessary. Anybody remember what is ln of 1? This is a special value for the natural log.
0.
It is 0, yeah. The natural log of 1, actually any log of 1 is always 0. That's a fact about the natural log, fact about logarithms, which maybe you remember, maybe you don't. Anyway, that one is just going to be all 0 because it's going to be 1/2 times 0 squared. What about ln of 1 over e? This is a little more complicated, but ln of 1 over e, that of course you could rewrite as ln of e to the minus 1. This is minus 1. Remember what ln means? It means what's the exponent that you need to get the thing on the inside. So when I see ln e to the minus 1, it means e to what power is e to the minus 1? The answer is minus 1. You could do that in your calculator if that was uncertain to you. But anyway, ln of 1 over e is minus 1. And so negative 1 squared is 1. I just get minus 1/2 for this whole thing. That's the area. So the first area, the one on the left, is 1/2. You're also going to find the area of the one on the right and then add them together. What do you think about that? I hope that that's helpful and clear. Any questions about how I did any of those? This one's tricky. Probably the hardest one on the homework, I would say.
So that one's supposed to be negative 1/2, but since you have to make it positive, you can just make it positive.
That's right. Yeah. So your job in this problem is to find these areas and add them together. The way you find them is by doing the integral. But the integral, just because of the way the integral works, when the area is below the y-axis, it's always going to report the answer as negative. And so when I do this integral, I will get the area, but I expect to have an extra minus sign. And so when I get the answer with a minus sign on it, I just make it positive, and that's the area. This one, it will not have a minus sign on it because when you do the integral of stuff above the y-axis, you get the true area, and it will already be positive. All right. Any more questions? We got 5 more minutes on the clock. I don't know if it's worth like splitting you all up. I wouldn't be able to come around and talk to everyone within 5 minutes. Here, I'm going to chat the link to the survey for the evaluation. I know only some of you are here today, so I'm gonna send this out tomorrow also for the stragglers. But if you can spare 10 minutes or so, please do it now. If you don't want to do it now, you can do it some other time. That's fine too.
You said the
any
answer to the first part was a half, right?
yes.
Okay, thank you.
Do you agree?
Yeah.
I've been wrong before, but I think it's a half.
I have a question. Is the class tomorrow going to be recorded?
Yes. Yeah. So I always record these Zooms and put them on YouTube. You usually get single-digit views, but it's easy for me to do it, so I might as well do it. And I'll do that for tomorrow's also. And I record both sections, and I always do different problems in the 2 different sections, so you can always watch both of them. You'll get different show each time. All right. I guess if there's nothing else, I'll see you all tomorrow. Hope you have a nice, pleasant lunch. I'm about to.